This is section 6 of Unit 4, Historical and Exponential Depreciation. Our quote is, "Driving a brand new car feels like riding around in an open billfold with the dollars flapping by your ears as they fly out the window." This is sort of a humorous explanation of what it means to drive a new car when the value is depreciating constantly. The objectives are to write, interpret, and graph an exponential depreciation equation and to manipulate the exponential depreciation equation in order to determine time, original price, and depreciated value. Some of the key terms from this section are historical data. This is prices from the past that a car was worth. Historical depreciation. This is using that historical data to determine how a car is devaluating. Exponential decay, this is value decreasing by the same percentage each year. So from year 1 to year 2, it might depreciate 10%. From year 2 to year 3, it depreciates 10%, etc. Okay? Exponential depreciation is exponential decay in the context of auto devaluation. Okay? So this is when we're talking about a car depreciating. Exponential regression is a way to model exponential depreciation. Geometric sequence, this is a sequence when consecutive numbers have a common ratio. In other words, they decrease by the same percentage each year. And then the common ratio, this is the number that can be multiplied by each term of a geometric sequence to yield a term that follows it. So what exactly do we mean by this word depreciation? If I were to take a number, say 100, okay, and consecutively take half of 100, which would yield 50, half of 50, which would yield 25, half of 25, which would equal 12.5, half of 12.5, which would equal 6.25, and half of 6.25 equals 3.125. Now I could keep going on forever. But if I were to graph that, notice what happens with the graph. It appears as though initially there's a big drop, then less and less and less and less. Okay? So it appears as though this is dropping significantly more the first year than the second year, but it's basically the same percentage. Okay, numerically it may change and be more the first each year and decrease the next, but percentage-wise, it's the same. So this is what we mean by depreciation. And specifically, this is exponential depreciation. So how does a car lose its value? Okay, we've talked a little bit about devaluation and what it means for a car, but what factors might contribute to a car losing its value? Some of these factors might be how much it is driven, okay? Do you drive a lot every single year? Where is it driven? Is it driven in the city? Is it driven in the country? Is it maintained? Okay? Etc. When, for example, where it's driven also might mean, is this in a place where there's bad winters, which can affect the car, or are you driving in Florida? Okay? So these are just some of the factors that contribute to a car losing its value, and to show that it might lose more of its value in certain places under certain conditions than in other cases or other conditions. So now let's look at some actual data, okay? So this is a car which was originally valued at $24,230. And as each progressive year, it decreased in value. Now, if we look at the ratios here, you'll see this is actual data. So these ratios aren't identical, but they're pretty close, okay? So it's pretty close to taking and decreasing the same percentage every year, all right? And then if we were to plot these points, we would get this type of a scatter plot here. And again, notice it is curving, it is not a straight line, and it is tending to flatten out as you get further and further out. So as I said, this is considered to be exponential depreciation, okay? And this can be represented by this formula here. Y is equal to A times 1 minus R to the X. A is the starting value of your car, okay, what you purchased it for. R is the percent of depreciation as a decimal. Remember, whenever we use a percent, we always have to use it as a decimal. X is the elapsed time in years, okay? And then Y is the car value after X years, okay? And this is considered to be exponential regression, and we can do that by using an exponential equation of best fit, which is y is equal to ab to the x. And if you look at this, what's in parentheses you can consider to be the b, the a, capital A is just the lowercase a. So this is the exponential equation that we're going to use for the line of best fit for our data. All right, so let's look at an example. Determine an exponential depreciation equation that models the data in the table on the previous page by using exponential regression on your calculator. I'm actually going to use Desmos rather than my calculator. All right, remember our original equation was of the form a times 1 minus r to the x, okay? And that's basically ab to the x. Well, I previously figured out what b was equal to. So if I set that equal to 1 minus r, I can solve for r. And if I do that, I come out with that r is equal to 0.08, which is approximately 8%. So that is the depreciation percentage for the 10 years of car prices as modeled by the exponential depreciation equation found in example 1. All right, let's look at example 3. Eamon purchased a 4-year-old car for $16,400. When the car was new, it sold for $23,000. Find the depreciation rate to the nearest tenth of a percent. All right, so we're going to use our familiar formula of y is equal to a, parentheses 1 minus r to the x. I know that the present value of the car is $16,400. The original price was $23,000. And we know that x is equal to 4 years. It's a 4-year-old car. So if I plug these into the original equation, I get this right here, all right? Now, if I divide both sides by 23,000, take the fourth root of both sides, and then set 1 minus r equal to whatever this comes out to be, and then solve for r, I come out with r equaling 0.0810772512, or approximately 8.1%. All right, example 4. A car originally sold for $26,600. It depreciates exponentially at a rate of 5.5% per year. When purchasing the car, Richard put $6,000 down and pays $400 per month to pay off the balance. After how many years will his car value equal the amount he paid to date for the car? All right, if I use our depreciation formula over here, okay, I have the original price of the car. I have the depreciation percent rate of 5.5%. And I know that x is in years, all right? Now, in terms of him paying off the card, he pays $400 a month, but his initial down payment was $6,000. So we have this formula here, y equals mx plus b. However, x in this case is in months. So if I convert that to years, I have to take and multiply that by 12. So our formula where x is in years is 4,800x plus 6,000. Now I've got two formulas here, okay? And basically what I'm going to do is I'm going to graph those two formulas and see where they intersect. And if I do that, I get a formula where this formula right here, the 4,800x plus 6,000, is this blue line. Notice it starts off at 6,000 and goes up continually. 4,800 times x, where the x-axis, this is in years. So each year you're going to pay off for $4,800 more, and this is linear. Now the red line represents this formula right here, which is the depreciation formula. Notice it is not a straight line, okay? It starts off at 26,600, then keeps decreasing at the rate of 5.5% per year. Now, the point of interest is this point here where they intersect. Where they intersect, that represents where the value of the car is equal to the amount that has been already paid off to date for the car. And if we look at that down here, okay, it's a little more than 3. In fact, it's about 3.3 years where the value of the car is equal to the amount that has been paid to date for that car. All right, here's another example. A car exponentially depreciates at a rate of 6% per year. Beth purchased a 5-year-old car for $18,000. What was the original price of the car when it was new? All right, so let's look at our basic formula that we've been using the whole time representing exponential depreciation. We're going to use this formula here. Well, the value of the car is $18,000, okay? We don't know the original cost when it was new, but we do know that it's decreasing at the rate of 6% per year, and it's been 5 years, okay? Now, if I just solve this, 1 minus 0.06, raise it to the 5th power, divide that into 18,000, I come out with the original new price for the car was $24,526.37. All right. Leah and Josh bought a used car valued at $20,000. When this car was new, it sold for $24,000. If the car depreciates exponentially at a rate of 8% per year, approximately how old is the car? We know it was used, but we don't know how old it was. So once again, we're going to use our familiar formula here, okay? But in this case, we don't know how old the car is. So basically, we're going to solve for x. Now, so if I plug in the current value, which is 20,000, the original brand new value was 24,000, the rate of depreciation was 8%, we don't know x. Well, if I take and solve these numbers, divide both sides by 24,000, figure out what 1 minus 0.08 is, I come out with 0.8333 is equal to 0.92 raised to the x power. Well, how do you solve an equation where the unknown is the exponent? Basically, you have to use logs. So we're going to take the log of both sides, all right? So notice we take the log of 0.833. Now I'm going to take the log of this, but remember, whenever we got an exponent, we can put the exponent out in front of the log. So basically, I've got the log of 0.833 is equal to x times the log of 0.92. Solve for x, log of 0.8333 divided by log of 0.92. I come out with x is equal to 2.19, or basically the car was a little over 2 years old. All right, our last example. According to an online company that supplies used car vehicle history reports, a certain make and model car has the following values based on usage. The original price of the car was $24,000, okay? So we start out at $24,000, and each year the value goes down. So if this pattern continues, what would the car be worth when it is 6 years old? So this is new, 1-year-old, 2-year-old, 3-year-old, 4-year-old, and this is 5 years old, but we want to know what it's going to be worth when it's 6 years old. All right, so if we compare the value after each year with the previous year's value, we find out that there's a ratio of 0.9 in each case. In other words, going from 1 year to the next, the value becomes 90% of what it was. Or we might say that in each case, the value drops 10%, okay? So that means that from year 5 to year 6, which is what they're asking for here, is going to be a 10% drop, or the value is going to be 90% of what it was in year 5 in year 6. So if I take the value for year 5, which is $14,171.76, and take 90% of it, or in other words, multiply it by 0.9, I get the new value in year 6 of $12,754.58.